Hello, welcome to Tenum Talks by Tenum. Tenum is an e-learning ecosystem that provides techies with a space to learn hands-on skills virtually via an e-learning platform with instructor support and guidance, as well as learning resources and kits needed. Tenum Talks are virtual engagement sessions for techies where we code, we listen, we share with fellow techies, we learn, and we grow together. I am your host, Doreen Chamweno. Welcome to Tenum Talks. Are you seeing my screen? No, you're not. Are you seeing my screen?
Oh, okay, now we are seeing it.
Yeah, so the idea is you're supposed to decode these 5 letters into the alphabetic whatevers. And then, you just either you say your answer out loud or you write it on the chat. So, give it a try as we wait for anyone else who's joining till 8:10.
Doreen,
Hey.
kindly repeat what exactly the game is about.
So unaona kuna gray parts, then there are darker parts. So you're supposed to match those darker parts into their respective places here. So for example, this first one, it should be T.
Okay, I see.
Yeah, so you do the same for all the others. Then now you see what is it in full.
Sawa.
Anyone who's done?
Okay, we cannot see all the letters. I see imefika T.
Umefika T.
P, Q, R, S, T, like sioni U, V, and the rest.
How come?
I also can't see the last one.
Really?
Yeah.
That's very weird. Could you try zooming out or zooming in, because it doesn't make sense? I'm seeing all of them on my phone.
Really?
Yeah, let me try. Yeah, JB also sees all. As Geoffrey has already said TPHIY. So let me go with him, then we do another one last one, I guess. We still have 2 minutes. So TP,
Okay.
let me decode. TPHLY. Yes, JB, you're right. Geoffrey, the I is a Y. So we can do one more. Are you now seeing? Are you seeing if you zoom in, zoom out, change rotation?
Yeah, see it.
You're seeing all the letters. Okay. Now one last one. Okay. Nicole and JB, NXQKM. Now and also Geoffrey, NXQKM. Okay. NXQKM. Yeah, that's great. So that's it. I think now I can welcome Regan for him to now get started with the talk and just tell us. Thank you, JB. Thank you. Yeah, so JB says it's a great game. Yeah. So anyway, I think we can now welcome Regan to talk about data structures and algorithm and just give us a brief introduction. I just saw his tweets on him mentioning that he would be conducting classes on data structures and algorithms for a week. And I thought with his experience, he may also help us in one or two ways so that we can be better at data structures and algorithms and just learn a few things. Yeah, so welcome, Regan. I think I should, if you're sharing your screen, I have enabled sharing. So welcome.
All right, thank you. Thank you, Doreen. Hi guys, how is everybody? I hope you're all doing okay. So my name is Regan Muthomi. I think I am a data scientist sometimes. Other times I'm a farmer. Yeah. Today we're going to be looking at data structures and algorithms, and we're going to learn how really the importance of data structures and algorithms, and also do time complexities of learn about extracting or deriving the time complexity of data structure given some code. Yeah, so that we learn how to write efficient computer programs that run in the minimal time possible. Okay, so welcome. And I have to mention, I don't have like a computer science background, so you guys don't ask hard questions, okay?
Noted.
That was a joke though. Okay, let me share my screen. So welcome to an introduction to data structures and algorithms. So this is just one of the classes that for the last 1 week, we've been having sessions helping guys learn about data structures and algorithms. We might have another one soon, so you might want to keep an eye on that. That is if you're interested in learning data structures and algorithms, because the first one is almost done. We're finishing tomorrow. Okay, so in this session, we're going to look at an overview of data structures and algorithms. We're going to look at time complexity, space complexity, and finally the big O notation. And if you have any question, feel free to, maybe you can raise your hand and ask. Whichever works for you, or maybe you can drop the question on the chat. So what is a data structure? Let's begin with that. A data structure is basically a way of organizing and storing data in a computer so that that data is easily accessed and manipulated. Okay, so data structure is basically how the data that your program is using is going to be laid out or is going to be stored in memory. By memory, I'm referring to your computer RAM. Yeah, I hope you guys, most of the guys here, at least you have a little bit of a programming background. So at least you know what a computer is, what RAM is, and all that. Okay. So a data structure is basically a way in which data is organized and stored in your computer so that it's accessed by the programs that you're running or by the program that you're building more efficiently. Okay. Different data structures have different layouts in which data is stored in memory. So we have a few examples of data structures. We have something like an array, which is just a sequence of values stored contiguously in memory. So they are stored sequentially, one next to the other. Yeah. So you're going to find a computer RAM, the RAM of your computer. A certain section of the RAM stores one array. So they are going to be in the RAM. The values in the array are going to be stored next to one another in some form of a sequence. And actually, let me open my whiteboard. I like illustrating stuff sometimes. Okay, right. So we say that data, depending on the layout that you choose or the structure that you choose, it's going to be stored in different layouts in your computer memory, right? And each data structure or each structure has its own advantages and disadvantages. Okay, so you might find a case where one data structure is a more efficient way of storing your data than the other. Doesn't mean the other one is a bad data structure. No, so we're saying here, the key differences between the data structures have to do with the trade-offs between how long it takes to populate the structure, how long it takes to add, insert, or find elements, and how large the data structure could be. Okay, so it has to do with one data structure having some advantages over other data structures in some cases, and then maybe the same data structure being the worst in another case. Okay, an example would be the array again. So in an array, we said that data is stored contiguously. So say this is like your RAM. So I'm not saying your RAM looks like this, but think of it as your computer RAM. So maybe somewhere here in this section of memory, you're going to store an array like this. And maybe these array stores numbers 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Sorry. So here we're saying that since this is an array, elements in an array are stored contiguously. in memory. And this is what contiguous means, one next to the other. Okay, I don't remember the spelling. Is it like that? I don't know. You can check the spelling, especially this part here. Okay, so this data structure is called an array, and it has its own advantages and disadvantages. One of the disadvantages would be maybe trying to locate an element in the array by using its value. That is a very huge disadvantage because you have to check through every element, and we're going to see why that is such a bad thing. But if you know the index position of that value that you're looking for, then your work becomes easier. And an array is good if you know the index position of the item or the element that you're looking for. Okay, and that's why we're saying that each data structure has its own advantages and also disadvantages. That's why when you're building a computer program, it's very essential that you select the best data structure to represent the data that you're working with. Sometimes you might need to use multiple data structures within the same system, which is also very, very okay. Now, we've seen what a data structure is. Yeah, it's a way of organizing and storing data in your computer so that it's easily and efficiently accessible. What is an algorithm? An algorithm is just a step-by-step set of instructions for solving a specific problem. And we use algorithms every day. Sometimes we don't even know we're using algorithms. Okay, the term algorithm itself has been around for a very long time, but algorithms in the context of computer science is what we are looking at in this case. But we as humans use algorithms every single day. An example, if you have a car, you want to move from point A to point B, right? How do you go about getting your car to move? Okay, you open the doors. So first you have to open the door, right? Because you're not getting into the car without opening the door. So you need to open the door. Some cars have these, especially the modern cars, you have to press on the brake first before you can start the engine. So the engine will not start before you press the brakes. So you press the brake pedal, start the engine, turn on the gears, step on the gas, and you're good to go. Okay, that's how you drive. That's how you get your car to start moving. It will not start moving like if you don't start the engine, right? And some cars, they will not start if you don't press the brake pedal before you start the engine. So it's like a step-by-step. It's a step-by-step process of getting your car to move. And that is what an algorithm is. Okay? Of course, in our context, in what we're talking about, it has to be implemented in code. Okay, so let's say you have a website, right? Where people are signing in, and maybe they're buying some stuff, or you're selling some stuff in your website, and before somebody buys something or accesses the resources that you're selling, they have to first log in or sign up. Okay, so how does that process work? How does that customer journey look like? So for you to get the user to sign in, or for you to get a user to buy something, because they have to sign up first or to have an account before they can buy. So they need to sign up, enter all their information, or the information that you require, then this information is going to be handled by the backend somehow. Maybe there are some validations that need to be checked. So it will go to the back here. There's some backend logic that is going to hand over the backend validation and so on. And also sometimes you might have set up validations on the front end. Then after validation, if there is a successful validation, you're going to save the data into the database. And then you can give the user feedback that their information or their account has been created. And now they can maybe go ahead and log in using the credentials that they've set up. And then after that, they can go ahead and make the purchase. Okay. So this is some sort of an algorithm, because it's a step-by-step of which you cannot reach to the purchase if you don't sign up. Yeah. And after sign up, your information will go through this journey. Then you get some feedback, and then you're going to be told to log in. Then you're going to log in, go to your account, and then you can make the purchase. So an algorithm is a step-by-step set of instructions on how to solve a certain problem. It could be a simple problem. It could be a very complex problem. Okay. So here's an analogy. You want to build a table, right? So you need to get the building blocks for building a table, which is maybe some pieces of timber, some nails, and some blue paint, because our table is blue, right? And then we're going to apply some set of instructions on how to build a table, right? You need to assemble your tools and use the instructions for building a table and build this particular table, right? The same case goes for data structures. The data structures are the building blocks of computer systems, software. But you have to apply some instructions for you to use the data structures to build whatever computer system that you're building. And these instructions, these are the algorithms. So you apply data structures on you apply algorithms on data structures to be able to get your final product, which is the computer system or the application that you're building. Of course, this table, you can try and build it using concrete, right? Instead of using timber, you might choose, oh, I'm gonna build a table out of concrete. Yeah, you're gonna be successful building such a table using concrete, but does it really make sense? Like if you live in an apartment or like you're 5 floors up, and you build a concrete table, good luck moving next time you want to move to a better apartment, right? So it is inconvenient, it is expensive, right? The same goes for data structures. So if for a particular problem, you choose the wrong data structure, and maybe also choose the wrong instructions, that is the wrong algorithm, you're gonna end up with a very inefficient product or a very inefficient system, okay? So choosing the correct data structures and applying them optimal algorithms for a problem is the difference between having a very, very efficient and quick system or having a system that is very sluggish and not very efficient. Okay, so for any problem that you're solving using code, remember to choose the correct data structure. Okay, and I would go as far as saying this. Take an example of this data set here. So this is, say, it is the average price of the Apple stock or the Apple stock for 2023. These are not the accurate prices for the Apple stock or Tesla stock, Tesla shares, or whatever you want to call them. So let's say this is the monthly average from January to May 2023. So what would be the right data structure? If you wanted to represent this data in code, what would be the best data structure for this? Let's look at an example. And I'm going to be using Python, but it should apply to all other languages. You just need to change the syntax, because all languages have some implementations of all the data structures around. Okay, so let's say we want to use an array to represent our data. So what do you need to do? Say, let's call these, let's call it a Tesla shares, like that. So you could use an array or a list. Yeah. So for every month, we're going to have the month. We're going to have a sublist or subarray, say January. And the price for January was 100, right? Then we're going to have another subarray here for Feb. And Feb was 102. Then we might have March. Which is, I think, 105. Then we have April, which is 104. And finally, we have May, which is 109. Okay. So then we can just output that. And there we have it. Okay. Now, say we wanted to access the price for the average price for April. How do we do it? Okay. How do we do it? Let's say that our data is not ordered. Yeah, it's not ordered like January, February, like that. Let's say February is here like this. Okay. So what if we wanted to get the value for April? We need to write a loop. So we might say for every month in Tesla shares, we're going to get if the first element in the subarray, that represents that month is equals to April. Oops. No, that first element has the index of 0. If it is equals to April, then we're going to print maybe the second element in that subarray with just the index of 1. So run this, and you see we get 104. But is this really the right data structure? When we look at complexity analysis, we're going to understand why this is not the best data structure to represent this data. Okay, so for now, let me leave it at that. And let's go ahead and now look at the big O notation, which is a asymptotic notation or mathematical notation used to estimate how execution time and the space requirements for a computer program grow as the input size grows. So how does your program scale given a huge number of inputs? That is what the big O notation seeks to estimate. The running time and the space requirement for your program. As the input grows, how does those two factors grow? How does time and space grow? Okay, time complexity measures how time grows as the input size of your program grows, and space complexity measures how memory usage of your program grows as the inputs grow. Most of the time, you'll not be concerned too. I'm not saying space complexity is not important. It is important, but most of the time you're going to be thinking about the running time, not the space requirement. And why? If you think about it logically, generally space is cheaper than computation. Yeah. Storage is cheaper. That's why hard drives are cheaper than processors, right? And you see how a hard drive is a massive thing, right? And a processor is a very small component, but it costs many times the cost of a hard drive or a hard disk or an SSD. Yeah. So space is cheaper than time. So most of the time you're concerned with the running time of your program. Because also, like if you have a very slow program, say you have a website that loads really, really slow. That is, for one, that is a very bad customer user experience, right? So somebody will come, look at it, give it a few seconds, it has not loaded yet, and they'll be gone. Yeah, so you're not going to have any traffic in your site just because it's slow. So the time that it takes for a program to run is very, very important. Okay. So big O notation seeks to estimate. It's not like an accurate measurement. It's a rough estimate of how much the running time and also the space requirement of a program grow as the inputs increase. Okay, or the number of inputs that program is using as they increase. How does time and space grow? We could think of it this way. How about we take a program and calculate the amount of time that it takes to run? Isn't that enough instead of having this whole thing called big O notation, right? You could measure time in absolute time, in absolute terms. You could say it takes 3 seconds or 3 milliseconds to compute or to run a certain program, right? Can we just do that and forget about big O notation? Of course, we cannot do that. Why can we not do that? Because depending on the hardware in your machine, the processors and all that, and also the other processes that are already running in your machine. Measuring the efficiency of a program in absolute terms, like milliseconds, is not a very good idea. It doesn't really make sense because you might have the same one program, you put it on your machine, it takes 22 milliseconds to execute. You put it on my machine, it takes 30 milliseconds to run. You take it to a different machine, it takes 10 milliseconds to run. Yeah. Because this is heavily dependent on the hardware components in a computer, and also the number or the amount of processes that are already running in the system. It could be, the system could be overwhelmed because it's running many other operations. Therefore, this program is going to run slower in that machine. Then you could have a machine that is really fresh. It doesn't have much background processes running or any other processes running in the background. So it will allocate a lot of resources to that particular program that you're running. Okay. So measuring time in absolute terms is not a very good idea for those two reasons. Okay, so what do? We seek to express the time complexity and the space complexity as a mathematical function or a mathematical notation, which is where the big O comes in. Okay, and big O measures the upper bound of an algorithm. This means worst case scenario. In the worst case, what happens to how does time and time, that the running time and the space requirement grow given a set of given input growth in the worst case scenario. Okay, that is what the big O notation measures, and we're going to see about what I mean by the worst case scenario. Okay. So let's go ahead. Before we look at the type. We look at some examples of big O notation. Let me go back to the coding example here. I want us to think of big O notation in this way. So let's say we have a program for finding the squares of a number. So we have a function here. I'm just going to use simple pseudocode function with two inputs, with one input, which is an array. So it will take the array, then get the squares for every number in that array. So we're going to have a loop, and inside that loop, we're going to square every number. And maybe we can return the square. Return the squares like that. Okay. So given an array of numbers, let's say we call our function using 1, 2, 3, we expect our function to return the squares of these numbers as 1, 4, and 9. Okay. Okay. So when you think about a big O notation, or when you think about time complexity, instead of thinking about the milliseconds and seconds and hours and all that, think of it this way. How many operations does the program need to perform? how many operations are going to be performed by that program. Because the amount of time taken is directly proportional to the number of operational, number of computations the program will need to perform. Okay, so if you perform 10 operations, that means you're going to take shorter time than performing 20 operations, irrespective of the hardware or the type of processes running in your computer. Okay. 10 processes or 10 operations are going to take shorter time than 20 operations. Okay, so in this case, because we are looping through every item in an array, we're going to repeat the square operation 3 times because our array size is 3. Okay, now if we pass in a bigger array, say now 4, 5, 6, 7, 8. If we pass a bigger array, we expect this body of the loop here where the calculation of the square is being performed, we expect that to be performed the number of times, or the number of repetitions will be equal to the number of times in this array. Okay, because we need to calculate the squares of these 5 numbers. Initially, the array was of size 3, it had 3 elements, but now the array is of size 5, so it's going to perform 5 operations. Okay, if you have an array of say with 1 million elements, so then these operations for calculating the square are going to be 1 million, right? So what do you notice in that scenario? We have, as the input size increases, the number of operations also increase, right? And this kind of relationship, we could call it a linear relationship. So you have time and we have input n. So this relationship is going to be something like this. And time here is going to be equals to an, n being the input size, plus a constant, let's say c. That is the equation of this relationship. And given this equation, now we can be able to extract the big O, or the time complexity of this kind of function. And how do we do that? The first step, if you have the function, the first step is to drop the constant. Sorry, you pick the fastest growing term, not the constant. The first is pick the fastest growing term. In our function, the fastest growing term among, so we have 2 terms actually. We have this an and we have this c. So given the input n, which term here is growing fast? C is not growing, it's a constant value. Okay, it never grows. Actually, C in regression, C should be this one. Right? Where the y-intercept, where the curve or where this linear line intersects the y-axis, and t is our y-axis in this case. So this is the C. It's a constant value. So the fastest growing term is this, because as the input size increases, say, I'm running out of space here. Say n is 5 and A is 2 and C is 3. So if we substitute these values in our equation, we're going to get n is 5, A is 2, so that is 2 times 5 is 10. So it's going to be 10 plus C, which is 3, right? Now, what if we increase n to 10? What do we get? 10 times 2 is 20, 20 plus 3, 20 plus 3. So which is the fastest growing term? Which given a change in the input values, which term is going to grow the fastest? Is it the first term, this one, or is it this one? Of course, it is the first term, someone that is going to grow faster. Okay, so we are going to pick the fastest growing term. So we're going to basically say t is equals to a n, because we dropped this, which is the lower term or the lowest growing term. Then the second step is drop constants. We're going to drop the constants. And the constants in this case that we are left with is A. A is the constant. It's not changing. Okay? Again, in math, A should be the slope of this equation. The change in Y or the change in T due to the change in N. That is what A is. It's a constant value. As long as this line is straight, it will always be one single value. Okay, so we're going to drop N. So, sorry, the constant, which is A. So we are left with N. Then we're going to introduce O. And then we're going to introduce O. And therefore, we're going to say the time complexity of this function is O of N, which is also called linear time complexity. Why is it linear? Because the time that it takes to run the program increases as the input size increases. That is linear relationship. One variable increases as the other one increases. That is linear growth or linear relationship. Therefore, this function for squaring an array of numbers has big O of N, which is a linear time complexity. And that is how you can mathematically derive the value or the time complexity of a computer program. Just think of time. Don't think of time as an absolute term, like the way we do, like how many minutes did you take in the shower? 30 minutes. That is absolute, right? But in this case, time is a mathematical function. It is not an exact number. Okay? All right. So given our function here, sorry, this is not actually a function. This is just, let's make it a function. I'm going to call it get price. Like that. Then I'm going to call get price. and we get 104. So what is the time complexity of this function? I want you to think of it this way. If this array size increase, let's say we added June, July, August, all the way to December, how would the operations here change? Would they increase as the input size increases, or how would that be? Let me know on the chat. What do you think? How do you think the time would grow or would change as this input size or the input of or the size of this array increases or decreases? What's the relationship between the time or the time in the context of the number of operations that we're going to perform or the number of calculations that we're going to perform with respect to the change in this array? Thank you very much, Sam. As the input size increases, the time also increases. Very correct. Because if right now the size of this array is 1, 2, 3, 4, 5. It's five items. So we are running in the worst case scenario. That's why I said the big O measures the upper bound of an algorithm. It is the best case scenario where we find the item that we are looking for as the first item. Okay. Say we were looking for January. Okay. Say we were looking for January like that. So January is the first element in this array. Okay. So we find it very fast. We don't have to go through the rest of the array. So actually we can say once we get that value, we can break out of that loop so that we don't go through the rest of the loop. Okay. But when you're thinking in big or perspective, don't think of the best case scenario. Don't ask yourself, wow, what if the item that I'm looking for is the first one? Does it mean I will perform only one operation? Of course, it is that possibility, right? But now you should also ask yourself, what if it's the last item? What if you are looking for February? Because February is the last one here. So you have to go through the entire array. You have to traverse the entire array to reach the value of February, right? So you're thinking in worst cases. The kind of how we say, prepare for the worst and hope for the best. We can hope that the item that we're looking for is the first one. Okay, because that saves, if we had a very big array, if we had a very big array, that saves has a lot of time because we don't have to traverse the whole thing. Okay, that is in the best case. In the worst case, it could be we have 1 million elements in the array, and the element that we're looking for is the last one, it's the millionth one. So we have to traverse that whole array until we reach the millionth item or the millionth element, then we fetch it. So always think, when you hear big O, think of the worst case. The worst case in our scenario here could be when we are looking for the last element, or the element that we're looking for is the last in the array. Okay? And now remember, I promised that we're going to come back and review this. So we have another data structure called a hash table. And for this case, a hash table is actually the best data structure to represent this data. Okay? So we could say something like this. A hash table in Python is actually the Python dictionary. You could say, let's call it Tesla hash. Is how you define a Python dictionary. A Python dictionary is what is commonly referred to as the hash table or the hash map. I'm going to keep copying these. Actually, let me copy all, make work easier. Like that. It's as simple as that. So accessing an element or trying to get the price of, say, February, we're just going to do this. So we're going to say, we can even define our new function, get price, get price to, then price, then we get the month that we're looking for, let's say January, like that. Then we can print the price. Then call our function, get price to. You see, this is 100, right? But now, how many operations did we perform? How many repetitions did we perform in this case? 0. We didn't write any loop, so we didn't repeat multiple times to find the item that we are looking for. So this time complexity is constant. Doesn't matter how many items you have in the collection, you're going to have a constant time complexity. And constant time complexity is O, big O of 1. Okay? Doesn't matter how many inputs you have, it's going to take constant time. The time that it takes when you have an array size or an input size of 1 or 5 is the same time it will take when you have an array or an input size of 20. So that time is constant because you're not having to perform repetitive or multiple computations within that function. So this function here has time complexity of big O of 1 because we are only performing this one operation and we get what we are looking for. And this is why you need to be able to use the right data structure, because this has the big O of n, that is the input size, the time increases as the input size grows, that is O of n. O of n is slower than O of 1. O of 1 is constant time. If you have 1,000,000, you have 1, you have 10, it will take the same time. With O of n, the time that it takes to run a program increases as the input increases. So ideally, the best running time for a program should be O of 1, constant. It doesn't matter the input, it takes constant time. Okay, by using the correct data structure, which is the hash table, we are able to knock down the time complexity of our function from O of n to O of 1, basically by using the correct data structure. Okay. So every time you're writing a software program, at the back of your mind, you should be asking yourself, if this function requires an input, some inputs, and this input might be increasing over time. Let's say maybe you're fetching data from a database, and this database is constantly being updated. Maybe people are creating an account with into that data. People are creating an account with your company or your service, and you're adding more subscribers to your product every day, so your database is growing. So if there's a function that processes that data from the database and maybe does some computations and gives you an output, so as you gain more and more users or more and more subscribers, how does the time that it takes to run that function take? How long does it take? Or like, how does the running time for that function increase as you gain more and more subscribers? Okay, so you should always have that at the back of your mind when you're writing any software project or any software program. Okay. So we can finish it off by looking at some common big O notations. But of one, we've looked at that is constant time. We have O of log n. That is where that is where the number of computations it decreased by half. If we had another session, we would look at an example of that using, or maybe go ahead and look at the binary search algorithm. It has the time complexity of O of log n. Linear time, we've looked at that. We also have linearithmic time, n log n, exponential time, 2 raised to the power of n. We also have things like quadratic, n raised to the power of 2. We have cubic, n raised to the power of 3, and so on. Okay? So n is the fastest. Like, that is why if you build a system with O of 1, that means there's constant time complexity. Doesn't matter how many inputs you put there, the time that it takes is going to be the same across any number of inputs. Log n is the second one, linear, then linearithmic, and so on. Okay? And that's it. But I want to leave you with this. So I have a function that finds duplicates in, you write a function that, so you're given this array. Five, 6, 2, 4, 7, 6. So you write an array, write a function. A function that checks for duplicates in the given array. Use with A big O of n squared. So n raised to the power of 2 and big O of n. So this is the worst performing implementation, and this is better. Okay. So try and do that during your free time. You can, if you're not a Python person, you can do it with maybe any other language, Java, JavaScript, whichever language you use. Should be the same. Okay. And with that, I guess I'm done, unless you have questions. I give it back to you, Doreen.
Okay, thank you. Yes, Sam. I see Sam has raised his hand.
Yeah, I'm raising my hand. Okay, Mr. Muthomi, that was a really great presentation. But I have a question. When first you mentioned arrays, you said that when you have an index of the particular item you want to maybe get, then it is like constant time. It is like that quick. But I don't know if I'm thinking too much, but it always puzzles me that with an index, let's say even an element is in the millionth index, right? But that still gives you a constant time. Like, doesn't the computer not like count from 1 all the way to maybe to the millionth index and then gets that item? What actually happens? I don't want you to give me the like all the details, but just an overview of how when you have an index of a particular item to get it its constant time.
All right, let me share my whiteboard again to explain that. So remember we said that if you have an array, you're going to the items are going to be stored contiguously in memory. So say, and this storage of storing an arrays in contiguously in memory is actually the Achilles heel of arrays. That's why you have other data structures like the linked list that addresses that. Maybe go read about that. So this is how the elements in an array are going to be stored. Say we have just a few of them. So let's say we have numbers or integers, 2, 7, 8, 5, 4, and 9. So what happens here is, let's say 0, 4, 0, 0, 0. That is the memory address of this element in your RAM. Then these can be 4, 0, 0, 8. Sorry, 4, 4, 0, 0, 4. And you know, an integer has 4 bytes. Okay, one integer has the size of 4 bytes. So you're going to store the 4 bytes between 0 and 4. Then this is going to be something like 008. Then this is going to be something like 400, 012. Now you know the drill, yeah? So what happens, let's say, because this is index 0, this is index 1, this is index 2, this is index 3, this is index 4, this is index 5. Okay. So what will happen, say you wanted to get the element at index number 2. Okay, this one. The item at index number 2. So what will happen? The computer already knows the starting address for the array, which is this one. This is where the array starts. Okay. So what it's going to do, it's going to take the index of 2, multiply by the size of an integer of 4, which is 8, and then it's going to add that to this starting address. So 4000 plus 8 is going to be 4008. And that is why it's going to pick the item that you're looking for at that address, 4008. So this operation, of course, remember we said that we are going to be dropping the list growing term. So this operation, this multiplication is a very negligible number, because we say big O is not an exact measure, it's a rough estimate. So you're not going to consider this multiplication of 2 by 4. What you want to know is this. So this operation is very minute to even consider. Okay?
Yeah.
Some?
Yeah.
So that is how that is why accessing an element by index has O of 1. But if you want to access by value, if you don't know the index, then it's going to have O of n, because now you have to go through every item, checking whether it's the item that you're looking for.
Understood. Well explained. Thank you.
All right.
Great. I also see Matthew Washira has raised his hand.
Yes, good evening, everyone.
Good evening.
Hello. Okay, first, congratulate and appreciate the efforts that you are making, and note that Muthomi is a good teacher. To add something on what he was sharing about the arrays, when I was learning C, that arrays they use memory addresses that are referenced using pointers. So to get the memory address, you use a relative address which is in a constant. Muthomi started by saying that that an array stores data in a contiguous manner. So that means if it is stored one after the other, to get an element at a particular index, it will be negligible. The complexity will be negligible, and that amounting to 1. The big O notation is 1. If I'm not wrong, I think it is about the pointers that are direct. Thank you.
Thank you, Matthew. I think Sam, you have your answer. You're satisfied. Thank you so much. Any other question? So let's remember the question you've been. Okay, Matthew. Yes, Matthew.
Yes, before I forget, I was asking, do you hold the meetups, the tech meetups?
Yeah, so every Tuesday we do data structures and algorithms. We start with an easy, then a medium, then hard, then a talk after. So next week we're going to do data structures, now the practice sessions. So every week we are doing a practice session on a given topic. Next week we'll be doing stacks and queues for our session.
And okay, I understand. Have you ever thought of making a physical one? That is what I thought I was asking. A physical one.
Physical. Maybe we do it in form of a hackathon. We're brainstorming on that in form of a hackathon, because I don't even think we are in the same location, all of us. So maybe if it's a hackathon, that's a one-time thing or occurs occasionally, not every week we meet up physically.
Okay, thank you.
But that's something that we can always see the possibility later on.
Okay, thank you.
Yeah. Yes, Alex?
Hi, can you hear me?
Yes, we can.
Okay. I wanted to ask, which particular language are you using? Are you using to do the sessions?
It's open. So since it's practice session, the idea is, as Regan was sharing, he mentioned that algorithms are processes of
Yeah.
how you're coming up with a solution.
Yes.
And then the language is just the syntax, right?
Mhm.
So when it comes to thinking about how you will solve it, we can all
Mhm.
think together regardless of the language we're using.
Yes.
Yeah. So now it's open in the sense that we form groups
Mhm.
dependent on the language you're using.
Mhm.
However, any language is allowed.
Okay. I think my question is, to be clear, I think Muthomi is covering the concepts, which up to that point I've gotten. But now, what about when coming now to the language specific? Because I believe most of the resources are usually Java, Python, or JavaScript.
Yeah. Yeah.
So if you want to actually understand a particular language, is that do you have that capacity to maybe can I request, or is it possible to maybe see you guys on the side?
Yeah, sure. And also, if you would like resources on a certain thing or a certain language, you can always share. Then anyone who has the resources, they can give you the resources they have. Yeah,
Okay.
so far, yeah.
Mhm.
So if you need any resources, you can always request for the
Actually,
resources.
I have the resources. It's just the understanding. I think I need, or rather, on my part,
to work
yes,
with.
people to actually work with. Yeah, specifically Elixir.
Elixir. Okay, so now who's doing Elixir here? Anyone? Maybe join the yes. Anyone?
Just to maybe contribute to the conversation.
Yeah.
I would like to ask Alex, do you have an experience with another programming language, or Elixir is your first?
No, actually do JavaScript. Mostly the front end. So what I'm trying to do is now basically move into the back end. And as much as I'm in a team and I've been working for 5 years, so I'm trying to transition into that space. But the concepts keep twisting, or rather they just keep missing in a way. I can write, but I can't understand when left to do. So that's why I'm trying to push myself to understand data structures.
Okay.
Yes.
That it shouldn't be hard because you already have a background in JavaScript. Like, okay, this is just an opinion, actually, not a fact. It's just an
I
opinion.
know. I understand.
Picking one language when you know another one is a little bit easier compared to like starting from scratch. And somebody on the chat is actually has actually dropped a good comment there.
Perfect.
LinkedIn search, there's a guy called Munavu somebody.
Mhm.
Maybe you can reach out to him and see if there's a way he can help or something. Just try.
Okay, no worries. Thanks.
Yeah, but for the
So,
sessions
Doreen,
as well. Yeah.
just a minute. I think I'm gonna drop off now.
Okay.
I have another meeting to attend.
Sure. I
Right.
hope everyone is good before Regan leaves. Okay. Sawa, thank you so much for joining, for sharing. And we hope to have you some other time on a different session, doing a different topic, maybe still in the same
Maybe
DSC.
data science. That's my thing. So if you
Okay.
find yourself discussing data science, maybe you can reach out.
Sure.
Right. Have a good one, guys. See you next time. Cheers.
Bye. Have a good night. Okay, so if anyone has any other question or any issue to address, otherwise we can meet next week. Okay. So yes,
Sorry. So the session is being recorded. Where is it being uploaded?
YouTube.
Okay. Same the tech.
Tenum.
All right.
Yeah. So I will upload it, then I'll share, because when you're registering for these sessions, you also add your email. I'll share
Mhm.
it with you via your email address once it's up.
All right.
Yeah.
Thanks.
Okay. Thank you, guys. Have a good night.
Good night.